All right, welcome. Thanks for sharing all this really cool stuff with us. Today, we're diving deep, kind of like into a vault, into how these seriously powerful AI things, the classification models make their decisions. They're everywhere, right? Big stuff like defense, healthcare, even the news we see. But how they decide on an outcome, that's the mystery we're tackling. So, in this deep dive, we're going to try to wrap our heads around a new method called CHIRPS. No, not the bird sounds. This is all about making sense of predictions, specifically from what they call random forest models. And we're going to try to do it without getting lost in the technical jargon.
Exactly. And it's becoming more and more important to understand this stuff, right? With AI being used for so much, national security, healthcare shaping what we see online, having some transparency is crucial. We're talking about models that predict if someone will pay back a loan or what's the best way to treat someone, big decisions. But if we don't get why they're making those calls, can we really trust them? How do we even know when things are going wrong?
All right, so let's break it down a bit. You mentioned random forests. For folks who don't spend their days with machine learning, what's a good way to picture this?
Think of it like this. You have a bunch of decision trees, like a whole forest of them, all looking at the same information. Each tree makes up its own mind, its own answer, and then the whole forest, they vote. Majority rules for the final prediction. And these random forests, they're known for being pretty darn accurate. That's the good news. But the catch is they're kind of like black boxes, you know?
Yeah.
Data goes in, prediction pops out. What happens in between? Total mystery.
And that lack of visibility, that's a real problem, right?
Right.
Especially in fields with a lot of regulations where sensitive information is at play.
Oh, absolutely. Like the sources you sent over pointed out, in industries with strict rules like finance or healthcare, where decisions based on AI can have a huge impact on people's lives, denying credit, flagging someone as a risk. You got to know why those decisions were made. There has to be a way to question them, right? And, regulations are even starting to catch up to this whole explainability thing. Plus, without understanding the why, how can you catch mistakes or figure out if the model is making biased decisions? It's really important.
Which brings us to CHIRPS. That's collection of high-importance random path snippets, if you want the full name. Even the name is kind of cool. So how does CHIRPS crack open this random forest black box when we're looking at a single prediction? What's the secret?
Well, the really cool thing about CHIRPS is it's laser focused. It's not trying to untangle the entire crazy complex structure of the whole random forest. It zooms in on explaining one specific prediction at a time. So let's say you have a piece of data, right? CHIRPS looks at all the different routes, the decision paths within the forest that led to that same final prediction, like tracing the steps of all the trees that agreed on the answer.
So it's ignoring the trees that voted differently,
Yeah,
just focusing on the ones that came to the same conclusion.
exactly. The idea is that the explanation should be super relevant to that specific case. If a path led to a different outcome, it's not part of this particular explanation. Makes sense, right?
Gotcha. So we've identified all the paths that contributed to the majority vote. What next? How does CHIRPS make sense of all these paths?
This is where things get super interesting. CHIRPS uses something called frequent pattern mining. Imagine a detective, right? Looking for the most common clues in a bunch of similar cases. CHIRPS does something similar. It goes through all those decision paths and finds the conditions that pop up the most, like if this piece of information is bigger than that value, that kind of rule. The ones that appear most often, those are the big players in the model's decision. They're like the smoking gun.
Ah, so it's finding what the majority of those decision-making trees have in common when they came to their conclusion.
Right on. And from these frequent conditions, these common clues, CHIRPS builds a simple rule, easy to understand. It usually looks like, if this and that and this other thing, then boom, this is the prediction. It's basically summarizing why the model decided what it did.
And this rule, it's not just floating out there on its own, right?
Mm-hmm.
The stuff you shared mentioned something about how reliable the rule is, how often it pops up, even scenarios where things could have gone differently.
You got it. So this rule, it comes with a sort of performance review. Precision tells you how reliable it is. If the rule says something's going to happen, how often does it actually line up with the random forest prediction? Like, is it a 50-50 chance or is it spot on 99% of the time? Then there's coverage. That tells you how many instances in your data actually fit this rule, gives you an idea of how broadly it applies.
Okay, makes sense. And the counterfactuals, what are those? It sounds like it helps you understand what could have happened if things were just a little bit different.
That's the really powerful part. Charities can tell you, hey, if we tweak this little thing in the original data, the prediction might actually flip. For example, let's take that adult income data from the research. The rule might be something like if someone has low capital gains and they're not married and they have less than 11 years of education, they probably make $50 or less. The counterfactual would then say, but if their capital gains were way higher, that prediction could change. They might actually earn more. It's like getting a sneak peek into what really drives the model's decisions.
That's super useful. The research paper you sent also mentioned an experiment, putting chirps head-to-head with other methods that try to explain AI decisions. What was that all about?
Right. So in the artificial intelligence review paper, they compared chirps to four other big methods: anchors, Bayesian rule lists, in trees, and defrag trees. All these methods are trying to make AI explainable, whether through rules or some other way.
And what did they find? How did chirps stack up against the competition?
The results were really promising, actually. The study found that the rules CHIRPS came up with were just as reliable, they call it precision, as the other methods when tested on new data. And we're talking high precision, like from 91% all the way up to 99%. But what was really interesting was that CHIRPS often had much wider coverage, meaning its explanations applied to a lot more of the data, anywhere from 4% to a whopping 54%, depending on the data set. That's a big difference.
So it's not just super reliable, but the explanations actually apply to a lot of the data. That sounds like a big win.
It is, and the researchers were also excited about how CHIRPS avoids two big problems with these kinds of explanations. Sometimes explanations can be too general, so they don't really tell you much useful. Other times, they're too specific, only applying to that one case you're looking at. CHIRPS tries to find that sweet spot by using some pretty clever math formulas designed just for this job of explaining individual predictions.
So chirps isn't just about getting the rule right. It's also about making sure the rule is useful, not too broad, not too narrow.
Yeah, finding that balance is key.
Okay, so just to recap what we've learned so far, chirps seems like a pretty cool new way to peek inside the decision-making process of random forest models, at least for individual predictions. It finds the important decision paths, spots the common patterns, and turns those patterns into a rule we can understand. And it even tells you how much you can trust that rule and what might change the outcome. Plus, early research says it's holding its own against other methods trying to do the same thing. We'll definitely have to dig into some of those technical details you mentioned, like those fancy formulas, a little bit later. But for now, I think we've got a good foundation.
Definitely.
So, as we put together this puzzle of understanding chirps, the big takeaway seems to be this. It lets us understand why a random forest model made a certain prediction by giving us a rule, an explanation that we can actually read and understand, which solves that whole black box problem we started with.
Absolutely. And figuring out the why behind an AI's decision, it's not just some academic brain teaser. Like we discussed, CHIRPS can do this cool thing. It can provide this what-if information. It doesn't just tell you why the model said what it did, but also shows you what tiny tweaks you could make to the input to potentially get a different prediction. This what-if analysis is really powerful. It helps you understand the boundaries of the model's decisions and where you might be able to step in and change things.
And you mentioned earlier some things that make chirps unique, things highlighted in the research. Can we dive a bit deeper into those?
Sure. One thing, like we touched on, is how CHIRPS tries to find that balance, right? The explanation needs to be specific enough to be useful, but not so specific that it only works for a tiny handful of cases. The researchers came up with these new ways of measuring how good an explanation is. They call them objective functions, specifically stability and exclusive coverage. Think of stability like this. If you have similar data points, will the explanation be similar too? You don't want an explanation that only works in one tiny corner of your data. And then there's exclusive coverage. That makes sure the rule is really telling you something unique about this specific outcome. It's like, this rule is important for this decision, and you won't see it popping up for other different decisions.
So it's like trying to find that Goldilocks zone where the explanation is just right,
Yeah.
accurate, and giving you a broader understanding without being so vague it's useless.
Exactly. Another cool thing is CHIRP's ability to give you those counterfactuals we talked about. It's not just about knowing the reasoning behind the prediction, but also about seeing what little changes could flip that prediction. This can be super valuable for understanding how sensitive the model is and what really matters most to it.
And how did chirps do compared to the other methods like anchors and those others in these specific areas like stability and coverage?
Well, the research you sent indicated that CHIRPS was generally doing a better job at balancing precision, stability, and coverage, especially in tougher situations like data sets with tons of categories or where some categories have way more examples than others. CHIRPS seem to handle these tricky scenarios better than some of the other methods. Like take anchors, for example. It might give you super precise rules, but those rules might only apply to a tiny, tiny fraction of the data. CHIRPS, focusing on stability, seemed to find explanations that applied more broadly without losing much reliability.
The material also talked about how well these methods could handle huge amounts of data, right?
Hmm.
Were there any problems there?
Yeah, that's a really important question, especially in the real world. The researchers mentioned that some of those methods that try to explain the whole model at once, like Bayesian rule lists, in-trees, and defrag truths, they had trouble when dealing with massive data sets. Sometimes they had to simplify the models a lot or limit their search for rules just to get them to work in a reasonable time. CHIRPS, because it's focused on single predictions, seemed to handle the big data sets better, although it wasn't always the fastest.
So some methods want to give you a big picture view of the whole AI, but they struggle when things get big and messy. But NERPS, by zeroing in on individual predictions, might be more flexible.
That seems to be the case. The researchers actually suggested that because those global methods sometimes need to simplify things so much, their explanations might not be truly reflecting the original complex model, more like they're explaining a simplified stand-in. And that raises the question, are these explanations really showing us what's going on in the real black box model?
That's a really good point.
Mhm.
If the explanation is based on a simplified version of the AI, you might not be getting the real story behind the decision.
Exactly. And CHIRPS sidesteps this problem by focusing locally, directly on the decision paths inside the original random forest. No need to simplify, so you get a more accurate picture.
So as we wrap up this deep dive, thinking about how AI is becoming more and more important in making decisions in all parts of our lives, how could methods like CHIRPS change how we interact with these technologies and how much we trust them?
That's the million-dollar question, and it's why this research is so exciting. If we can truly understand why an AI system tells us to do something, whether it's approving a loan, recommending a treatment, or flagging a risk, it could completely change our relationship with AI. Imagine not having to blindly trust a mysterious system, but actually being able to see the logic behind its decisions. That means we can spot weaknesses, find unexpected patterns, and build trust based on real understanding. Think about it. You could understand why an AI denied your loan application and even see what you could change to get a different result.
It's like going from a just trust me situation to a real partnership with AI. That's a powerful thought. Thanks so much for walking us through CHIRPS. It definitely gives me a lot to think about.
My pleasure. It's fascinating stuff, isn't it?
Absolutely. And for all of you listening, keep those questions coming. We'll keep digging into these topics and trying to make sense of this amazing world of AI, one deep dive at a time.